Welcome to number theory. Today we are going to explore Euler's theorem. Imagine a magical clock where if you spin the hands a very specific number of times, they always snap back to the exact starting position. This mathematical snapping back might sound like a neat party trick, but it is actually the hidden engine powering the security of the entire internet. Let us dive in and see how it works. Before we state the theorem, we need to understand two simple ideas. First, co-prime numbers. Two numbers are co-prime if they share no common ingredients or factors other than 1. For instance, 8 and 9 are co-prime. Second, we have Euler's totient function, written as phi of n. This simply counts how many numbers smaller than n are co-prime to n. If we look at the number 10, the numbers 1, 3, 7 and 9 share no factors with 10. Since there are 4 such numbers, phi of 10 equals 4. This function is the key to our magical clock. Now that we understand the totient function, let us look at the theorem itself. Euler's theorem states that if you take a base number a, raise it to the power of phi of n, and divided by a modulus n, the remainder will always be exactly 1. This only works if a and n are co-prime. Conceptually, this formula acts as a guaranteed shortcut. Instead of calculating ridiculously large numbers, we know that multiplying a number by itself this specific number of times will always land us exactly one step past a multiple of our modulus. If you increase the modulus n, the totient power phi of n also changes, shifting where this reset occurs. Before we move on to the proof, let us see this with a concrete example. We want to find the remainder when 3 to the power 4 is divided by 10. First, we identify our given values. The base is 3 and the modulus is 10. We must check if they are co-prime. The factors of 3 are 1 and 3, and the factors of 10 are 1, 2, 5 and 10. They share no common factors other than 1, so we can safely use Euler's theorem. Next, we need our totient function for 10, which we already found is 4. Now that we have our totient value, we can plug everything into the formula. We substitute our base of 3 and our modulus of 10 into Euler's theorem. The theorem guarantees that 3 raised to the power of phi of 10 will leave a remainder of 1 when divided by 10. Since phi of 10 is 4, this tells us directly that 3 to the power of 4 leaves a remainder of 1. We can verify this manually. 3 to the 4th power is 81, and 81 divided by 10 gives a quotient of 8 with a remainder of exactly 1. The theorem works perfectly. That first example was easy to verify, but this formula we just saw leads us to a much harder problem where calculating the number directly is impossible. We need to find the last 2 digits of the massive number 7 to the power of 2022. Finding the last 2 digits of any number is mathematically identical to finding the remainder when that number is divided by 100. So our base is 7 and our modulus is 100. Since 7 is prime and does not divide 100, they are co-prime. Euler's theorem is the perfect tool for this job. To use the theorem, we first need to discover the reset point where the remainder becomes 1. We do this by calculating phi of 100. Using the standard formula with the prime factors of 100, which are 2 and 5, we find that phi of 100 equals 40. This means there are exactly 40 numbers less than 100 that are co-prime to it. According to Euler's theorem, raising our base of 7 to this power of 40 will leave a remainder of 1. This gives us our magic reset point. 7 to the power of 40 is congruent to 1 modulo 100. Now that we have our reset point, we will break down the massive exponent 2022 into chunks of 40. We divide 2022 by 40 and find it goes in exactly 50 times with a remainder of 22. Using basic exponent rules, we rewrite our original problem to separate the 50 groups of 40 from the leftover 22. Because we are working modulo 100, we can completely replace 7 to the power of 40 with the number 1. 1 raised to the power of 50 is still just 1, so that entire massive chunk simply vanishes, leaving us with just 7 to the power of 22. We have successfully reduced the terrifying problem down to calculating 7 to the power 22 modulo 100. While this is still large, we can break it down further using squares. We know 7 squared is 49. Next, we square this result to find 7 to the 4th power, which is 2401. Because we only care about the last 2 digits, we can drop the 2400 and just keep the 1. This is an incredibly lucky break. We have discovered a much smaller accidental reset point. 7 to the 4th power is congruent to 1 modulo 100. With this new shortcut, we can finish the problem instantly. We rewrite our target, 7 to the power of 22, using groups of 4. We can fit 5 groups of 4 into 22, which takes care of 20 of the powers, leaving just 7 squared left over at the end. We replace 7 to the 4th power with 1, and we replace 7 squared with 49. 1 to the 5th power remains 1, so we are left with 1 multiplied by 49. The final result is 49. Physically, this means if a supercomputer calculated this massive number, the very last 2 digits printed on the screen would be 49. Now that we have used this formula to solve a massive problem, let us understand where it comes from. To truly understand why Euler's theorem works, we must prove it step by step. We start by gathering all the numbers smaller than n that are co-prime to n. Let us call this collection of numbers our special set. Because there are exactly phi of n of these numbers, we can list them out as R1, R2, all the way up to R phi of n. Next, we take our base number, a, and multiply it by every single number in this special set, creating a brand new set of numbers. Let us visualize what just happened to our set. Here we see a diagram representing multiplication modulo 10. Using our earlier example where the base was 3, the circles contain our original co-prime numbers 1, 3, 7 and 9. When we multiply each by 3 and take the remainder modulo 10, 1 becomes 3, 3 becomes 9, 9 becomes 27, which reduces to 7, and 7 becomes 21, which reduces back to 1. The magic of modulo arithmetic is that this new set is actually just the old set in disguise. No two new numbers leave the same remainder, so we get the exact same list of original values, just shuffled into a different order. Since the diagram showed us that the new set leaves the exact same remainders as the old set, multiplying all the numbers in the new set together must leave the same remainder as multiplying all the numbers in the old set together. On the left side of our equation, we multiply all our new terms. On the right side, we multiply all the original terms. The congruence symbol confirms both massive products leave the identical remainder when divided by n. Because there are exactly phi of n terms in our set, we have multiplied a by itself phi of n times. We can factor this a to the power of phi of n out to the front. This brings us to the final step of our derivation. Notice that the exact same product of r values appears on both the left and the right side of the congruence. In modulo math, we can only cancel a number from both sides if it is co-prime to the modulus n. Since every single r value was specifically chosen because it is co-prime to n, their total product is also completely co-prime to n. This means we are mathematically allowed to divide both sides by that massive product. When we cancel it out from the left side, we are left with just a to the power of phi of n. When we cancel it from the right, we are left with exactly 1. Hence proved, we have derived Euler's theorem. So, we have proven that Euler's theorem holds. This brings us to why this matters in the real world. Euler's theorem is not just a clever trick for math competitions. It is the foundational pillar of modern digital security. The most widely used encryption system in the world, known as RSA encryption, relies entirely on this theorem to scramble and unscramble data. When you send a secure message, your computer uses a massive modulus and a public exponent to lock the data. The only way to unlock it is by knowing the secret value of phi of n, which allows the receiver's computer to use Euler's theorem to reverse the process. It transforms abstract number theory into the shield that protects the global digital economy. Let us wrap up what we have learned today. Euler's theorem provides a powerful shortcut for finding remainders of massive exponents. We learned that any number a raised to the power of phi of n will leave a remainder of 1 when divided by n, as long as a and n share no common factors. By acting as a mathematical reset button, it allows us to chop impossibly large calculations down to manageable sizes, as we saw with our massive exponent example. Finally, we saw how this elegant rule of clock math is the invisible engine keeping our modern digital world secure. You have now mastered the core of Euler's theorem.